organizers for inviting me, and it's a sort of a funny situation to be in. I'm talking about a subject that I'm not actually actively doing any really research on right now, and most of the issues are old. Of course, they're becoming relevant again in the context of what we are and aren't seeing at the LHC. So it's worth talking about them to some extent. And also, I've been giving this kind of talk many times over the course of the past few months. And looking at the participant list of this meeting, I realize almost all of you have seen some version of that talk. So I decided to do something different today, partially because I remember when I was a graduate student, all those old farts at conferences who would give the same stupid talk over and over and over again. And I promised myself I would never be that old fart. So I may be in other ways, but if I catch myself, I'll try to stop doing it. So this is going to be a somewhat different talk. It's going to be a Blackboard talk, partially because I want to encourage it to be informal. It can go off in various directions depending on the sorts of questions people ask. So please interrupt at any point. And finally, I just want to say one aspect of it. I mean, why should you listen to me about naturalness? None of us have been right about what's going on at the weak scale. So why should you spend an hour, if you're lucky, listening to me? Well, no good reason. No good reason. What I can say, having thought about it, is I think I'm tied with Howard Georgi and Savas Simopoulos for having at least theoretically solved the hierarchy problem the most number of times. So that means that you know, I'm a card-carrying hierarchy problem solver. And also, I'm one of the people, like 10 years ago, one of the very few people who thought and talked openly about the possibility that what we might see at the weak scale isn't natural. I find it very amusing and interesting that that possibility is getting tossed around like it's a totally reasonable thing. These people weren't around 10 years ago when I was giving talks at conferences like this and people literally screaming at me. I mean, no exaggeration, for daring to raise such a possibility. So I've been on all sides of the issue, okay? And so the answer to the question, does naturalness matter? Well, we'll come back to it again. Of course it matters. I think it's the absolute key, most fundamental question that we have to come up with some sort of answer to at the weak scale. But I don't know. I don't know how it's going to go. I vacillate on my feelings about it, but the feelings are irrelevant. We're going to get some indication from nature soon enough. The other thing that I wanted to do in this talk to make it a little bit different is there is a sense a little bit out there, especially from people who have not thought about these things deeply, that, well, there was this community beyond the standard model builders who said we for sure have to have naturalness and we're for sure going to be supersymmetry probably. And now that we haven't seen it and we're probably not going to see it, these guys were totally smoking crack the whole time. Maybe we're thinking about everything totally wrong. Now some of them are saying it's fine-tuned or anthropic. That's an act of absolute desperation. It's probably something no one has ever thought of. Why don't these people go around thinking, deeper thoughts about it rather than just spewing this nonsense? And so what I want to tell you, actually, I went back to my notes. I stopped, very consciously, I stopped trying to solve the hierarchy problem on April 5th, 2004. And I stopped solving hierarchy problem after that. But I found in a basement somewhere all my notes from before that period. And I went and I looked, and it actually, in the notes, there were 14 attempts at solving the hierarchy and the cosmological constant problems. Okay? Very few of them ended up in print, because most of them don't work. But it's not true that none of us have thought about, totally crazy other possibilities. And I'm going to do something very dangerous in this talk today and tell you about some of them. No way in hell am I going to tell you about all 14 of them, because some of them, you might want to institutionalize me afterwards for. I'll talk about the saner ones which don't work. But just to give you an idea, because you might also have, maybe someone will be able to pick it up and do something with it. Anyway, so that's the goal of the lectures. And I'm going to spend very little time on super duper introductory material as well. So we can get on to more interesting things, but So the better title is maybe Naturalness and its Discontents. And the first thing to say is that the discovery of the Higgs is absolutely critical, not just for this discussion, but critical for everything in our field. It's not just something that we're hyping up for ourselves or for the general public. It's a watershed moment in our subject. For the first time in our history, we finally have a theory that we know describes nature at accessible energies and which can be extrapolated to exponentially higher energies than the energies that we're at. That has never, ever been true before. There have been bits and pieces. QED was complete and could be exponentially continued up to where it hit a Landau pull, perhaps. But right as people were figuring that out, they saw the strongly interacting mess of particles. So there was some other stuff that they had to figure out. At every single point in the last 100 years, we've had a provisional understanding of nature, but that provisional understanding could not even be extrapolated more than a factor of 5 above the currently available energy scales. We were always in a situation where we knew there was a scale where something absolutely had to happen based on general principles of relativity and quantum mechanics. Discovering the Higgs for the first time, we're in a different situation. Okay? So for the first time, we have a theory that does not that works, that describes what we've seen, and which does not predict its own demise, at least to exponentially higher energies than we have been. The other important thing about the Higgs is it's a scalar, it's a spin zero particle. And we've never ever seen that before. We've never ever seen in nature an elementary spin zero particle, which can, again, which looks point-like on scales exponentially higher than its mass. Of course, we haven't been to exponentially higher energies yet, but it's conceivable that the Higgs is something that looks point-like on scales exponentially higher than its mass. Now, why have we never seen this in nature before? Right? The answer is naturalness. So this is actually where naturalness came from. Okay? Naturalness explains why we've never seen anything like the Higgs before. Of course, we have one vacuum of our universe, but we can engineer lots and lots of effective field theories in condensed matter systems. They differ from our effective field theory of the vacuum in our universe because our vacuum is relativistic. But at least from the conventional Wilsonian picture of quantum field theory, this isn't for this purpose, it's not a humongously big difference. Maybe these issues about relativity and space-time become important as we get to the Planck scale, but there's no reason for them, apparently, to play a significant role at much longer distances. And so all over the place, we have tons of effective field theories that we can engineer in laboratories. And not one of them do we see in a state of nature a light scalar field. Why? It's because it takes fine-tuning to keep the scalar light. Stupid. Okay? That was Wilson's argument. And what's so special about scalars? What's so special about scalars? It's a very simple calculus. Why is it okay for photons to be massless? Why isn't it a big crisis of theoretical physics that photons are massless? The answer is that 2 is not equal to 3. Okay? A massless photon has 2 helicity degrees of freedom. A massive spin 1 particle has 3. And that's why it's okay for there to be massless particles. The existence of massless particles is robust. It's robust to any small modification you might make to the physics because you can't generate a degree of freedom out of the blue. Okay? So that's why massless photons. Now, you can ask, why do we have massless particles at all to begin with? That's also a very good and deep question. But their masslessness is not something which can be perturbed by messing around with a theory a little bit. Okay? Notice I didn't once say the word gauge invariance. Gauge invariance doesn't exist. And it's really putting the cart before the horse. Because we have massless particles, we as poor theoretical physicists find it convenient to use the words gauge symmetry to describe it. But there's actually, gauge symmetry doesn't exist. It's a figment of the theorist's imagination. What really exists is that 2 is not equal to 3. And it's because 2 is not equal to 3 that we can have massless photons. It's because 2 is not equal to 5, which we can have massless gravitons. But the argument breaks down for a spin 0 particle because 1 is equal to 1. And there is no discontinuous difference in the number of degrees of freedom for a massless and a massive spin 0 particle. Okay? So you would think that there's absolutely no reason why the mass shouldn't be at the natural short distance scale of the theory where the physics is defined and it descends from, and that's the hierarchy problem. The technical way, slightly more technical way of doing the calculation is to sum of a half h bar omega for every particle mode in the universe. And remember that the mass of, so this is the integral d cubed k for the energy density, d cubed k of a half square root k squared plus m squared for bosons, and a minus a half square root k squared plus m squared for fermions. And if we remember that the mass of the bosons is g times the VEV of the Higgs, the mass of the fermions is some Yukawa couplings times the VEV of the Higgs, then if we expand the sky, we get one piece, which goes like an ultraviolet cutoff to the fourth. We get another piece that goes like things like differences like this times h dagger h and so on. And these are our problems. That cutoff to the fourth is the cosmological constant problem. And this is the hierarchy problem, showing that quantum corrections do what you would think they should do. There's no reason for them not to do, which is to give large corrections to the mass of scalars. Now, often people say, people focus a lot on quadratic divergences as the sort of harbinger of the hierarchy problem. But quadratic divergences really aren't the point. They're related to the point, but they're not the point itself. After all, every time you have power divergences, it tells you that that quantity that you're computing, this thing that we're computing, precisely because it's power divergent, it's totally uncalculable given the physics you have, given the low energy physics. You have a set of, in the standard model, the mass squared parameter of the Higgs is incalculable. The fact that it's power divergent is one indication of that. And so you could take the attitude, well, it is what it is. It's some parameter of the theory. I go out and measure it from experiment, and that's it. That's a perfectly fine attitude. It's a perfectly correct attitude. This is why it took people 5 years to believe there was such a thing as a hierarchy problem. People like Sidney Coleman went around saying, I don't see a hierarchy problem. Who cares? There's just some parameter in the, there's some parameter. I have to measure it until it agrees with experiment, and I'm done, right? And that's correct. The hierarchy problem, or the fine-tuning that we'll talk about more, is not like other problems we've faced in physics. It's not, for example, like the problem of strong WW scattering before we discovered the Higgs. There, really something had to happen. Otherwise, unitarity is violated. Okay? There's a physical scale involved. It's not like the problem of quantum gravity, which is, by dimensional analysis, the identical problem. Where graviton-graviton scattering, or any kind of scattering amplitude, actually becomes strong at the Planck scale. Something has got to give. Something's got to change. Those are physical problems you can do nothing about. They must be solved. The hierarchy problem has always had a different character. Okay? There is no inconsistency with the general principles of relativity and quantum mechanics to have the Higgs as light as we like compared to the Planck scale. The problem is something else that this quadratic divergence is a harbinger of, which we'll talk about a little bit in a second. By the way, this is just a small comment for maybe the few experimentalists who haven't realized this, who haven't thought about this. There's a big difference, you see, between these power divergences and logarithmic divergences. Power divergences, by their very nature, are totally dominated close to the cutoff. And that means that's exactly where we don't understand the physics well. That's why they're not calculable. Okay? There's something that's getting bigger and bigger and is biggest where we understand the physics least. A logarithmic divergence is totally different. So let's say a power divergence, like for the hierarchy problem, is dkk. A logarithmic divergence is dk over k. And that means it receives equal contributions from all scales, from the high energy scale to the low energy scale. Logs are not a property of just what's going on at high energies. They're a property of everything in between, the high and the low energy scales. And that's why they're a critical part of the low energy theory. They're a critical part of the renormalization group. They're a critical part of Wilson's way of thinking about quantum field theory. And they're totally different. So it's not like we pick and choose which divergences we like. Logarithmic divergences are totally physical. They're crucial. They have lots of important physical content. Power divergences have no physical content. Okay? They are just purely reflecting uncertainty about what's going on in the ultraviolet theory. So why do we think there's a hierarchy problem then? The reason we think there's a hierarchy problem is that this power divergence is indicating an extreme ultraviolet sensitivity to what the mass of the Higgs is. So that whether you imagine that it's just the Higgs and nothing else all the way up to very high energies, or you add a very massive particle interacting with the Higgs up at the UV cutoff, any guess you make for what's going on at the UV cutoff, you make different guesses, you'll get wildly different answers for the mass squared parameter of the Higgs, and they'll differ by something of order the cutoff squared. So that cutoff is a measure for the sort of typical size for the Higgs mass you would expect. But the hierarchy problem only becomes really sharp if you try to ultraviolet complete the standard model into a theory where the Higgs mass becomes calculable. Okay? In the standard model, it's not calculable, precisely because it's power divergent. It's a parameter of the theory, and it's not calculable. But we can think of ultraviolet theories where the Higgs mass does become calculable. I'm talking about the mass squared parameter. Okay? The Higgs mass squared parameter becomes calculable. And there's a slew of them. The most obvious one, which can't be the real world for various reasons, Lorentz invariance, gravity, and so on, but a very obvious one, which is where these ideas came from, is to imagine putting the theory on a lattice. Okay? You take the standard model, you put it on a lattice, or you even put the scalar part, you put it on a lattice, and you ask. You just take the Lagrangian, you put it on a lattice. Now the Higgs mass squared is calculable, everything is finite. And what does it take to get the Higgs mass small? The answer is you have to make insane adjustments, the 32 decimal places, the usual tuning that we talk about, in order to keep the Higgs mass 16 orders of magnitude lighter than the lattice spacing scale. Okay? So we can just see it clear as day. But there's lots of other examples. The Pion is a good example. The charged Pion is a good example of a scalar that's actually point-like on the scale of its mass, up to energies that are 5 times its mass, or 5 to 6 times its mass. So why is the charged pion light? Well, we understand why the charged pion is light. Charged and neutral pions are light because they're Goldstone bosons. So we could imagine that. Could scalars be light because they're pseudo-Goldstone bosons? Okay? That's a nice UV completion of a scalar. And the answer is they can be, but here again, we can calculate what the mass of what the scalar or the Higgs would be in every such model. And in every such model, the mass that we get is some number, g squared times cutoff squared, where this is the mass of the first new states. And the coefficient out in front is just some number of order 1. Okay? So once again, so for instance, in QCD, there's this contribution to the mass squared of the charged pion from the loop of the photon. This is identical to the hierarchy problem diagram for the standard model. So any mystical words you want to say about forgetting about power divergences and so on, say them equally well for the charged pion as you say it for the Higgs. And you could say that and miss the opportunity to really understand some nice physics. Okay? Because you draw that diagram, you cut it off at the mass scale of the rho meson, which is where the new physics comes in, and you get about the mass splitting between the charged pion and the neutral pion. Okay? So this is a great example where, indeed, there's a light scalar. It's light because it's a pseudo-Goldstone boson, but it's not much lighter than the place where the new physics comes in, as dictated from what we always do, which is to stare at this diagram and make an estimate for what the mass is from taking that quadratic divergence and cutting it off at the scale of new physics. Okay? So here, too, if you wanted to make the charged pion 1,000,000 times lighter than the rho, we could only do it with extreme fine-tuning in the underlying QCD theory. And we can see it's calculable now. We can see the tuning that we have to do. Okay, there's an example which is dual to this, or very closely related to it in many ways. To imagine that the Higgs is the 5th component of a Gage field. Okay, so imagine that you have a scalar, that you have a 5th dimension, and you have, let's say, just to keep it simple, we have a non-abelian Gage theory. But as I go to low energies, I get a 4-dimensional Gage field, but I also get the 5th component of the Gage field, which from a 4-dimensional point of view, I don't know the circle is there. It just looks like some scalar field in the adjoint representation. Once again, I draw exactly the same hierarchy problem diagram. Once again, in the low energy theory, it's not calculable. But in the high energy theory, it is calculable, because when you go to very short distances compared to r, you see that this is a Gage field, and so it's massless in the 5-dimensional sense. So this is a beautifully calculable quantity, and what we find for the mass is exactly what you'd expect. It's, once again, it's the g squared of the 4-dimensional theory cut off by the scale of the new states. Okay? So yet another example, string theory. Okay? We can have non-supersymmetric strings. These give a size in the familiar way. Okay? Everything's a loop. Everything's a string with some size. It can be totally non-supersymmetric, and once again, you can calculate the potential for scalar fields like the dilaton or other scalars. And once again, you find the calculable answer you get from the string theory is some order 1 number times the string scale squared times the g squared. Okay? So every single time we can make it calculable, and of course we can make it supersymmetric. Okay? If it's supersymmetric at very short distances, we can make the Higgs mass squared calculable. In every single ultraviolet theory anyone has ever imagined, where the Higgs mass becomes calculable, getting the Higgs lighter than the scale of new physics requires the extreme fine-tuning that we guess at from the presence of this power divergence in the low energy theory. Okay? Those are the theories where the hierarchy problem is sharp. Right? In those larger completion where the Higgs mass is calculable, you can identify explicitly the tuning that is needed. And when it happens over and over and over again, you start thinking it may be a general principle. Now, let me immediately give a possible counterexample. So this isn't even one of the 14 attempts, not all of which I'm going to tell you about. But let's say someone handed you, just for fun, let's say someone came up with a new UV theory. They didn't tell you what it was, but they said, look, it's amazing. I calculate the Higgs mass in this theory, and there's the usual g squared times the scale where the new particles come in. But there's a coefficient, and I calculate, and the coefficient is 1 over 196,884. Okay? Well, that would be interesting. That would certainly explain the LHC results so far, right? Okay, that would be no problem. Now, but if someone told you that, you would say, oh, come on. You know, of course, you've done some kind of fine adjustment. Where from your underlying physics, where from the underlying theory can you possibly get that huge number unless you put it in by hand, right? You put in this big number, you're doing some tuning and some adjustment by hand, right? And the answer is no. Well, I don't know what the physics theory is, but this is well known and happens in mathematics all the time, that questions that don't have any big or small numbers in them have answers that generate humongous numbers in them, like that. This is a very famous number. It's the answer to a very simple question that complex analysts asked in the 1800s. Complex analysts asked in the 1800s, people like Jacobi and his friends, asked what kind of functions of the complex plane you could write down that were invariant. So this is the complex plane tau, under two transformations. Tau goes to tau plus 1, and tau goes to minus 1 over tau. This is so-called the generators of 2 by 2 linear transformations with integer coefficients. OK, I'm just writing it down just so it's clear. Nowhere in here, maybe there's a 2, OK, but nowhere in here do I have a particularly big or small number. All right? And so that's a perfectly nice question. By these transformations, you can actually map every point in the complex plane into what's called the fundamental domain, which is some region of the complex plane, real tau, imaginary tau that looks like this. And now the task is you want to find all functions which are invariant under this. So the task is to find a function, a holomorphic function j of tau, which has the property that it takes any point in this fundamental domain to a given complex number. So that j of tau equals a given complex number c has a unique solution, back and forth. Well, this is the problem that Jacobi solved. And it's a beautiful modular elliptic function. And this is the answer, actually, for what it turns out to be. OK, where q is e to the 2 pi I over. All right, so this is the answer to a beautiful math problem with no big or small numbers anywhere. And the answer has this humongous number in its first non-trivial coefficient. Okay, that's just a constant. That's not very important. This is the first non-trivial thing, and it's a huge number. The next one's an even huger number, and so on. Okay, where did these huge numbers come from? I don't know. Math knows, right? And so, by the way, those huge numbers are not unrelated to the 26 dimensions of string theory, which is another case where a relatively large number comes out of nowhere. You say things are like little loops of string, and then tuck, 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 26. Okay, so this is known to happen. Okay, so it's not impossible that the underlying there's some underlying mathematical formula with no big or small numbers that creates huge things like that. There are more even, I chose this example because it's slightly related to physics in other contexts. There are even more abstruse things that you could choose. There are certain Diophantine equations like a to the fourth plus b to the fourth plus c to the fourth equals d to the fourth, where the first non-trivial solutions start with very long numbers, many, many, many digits, right? But they have counterexamples to them. So if you could find a theory where the Higgs mass is calculable and for some reason in units of the cutoff, it's given by 1 over the first non-trivial coefficient of the J function, you've made progress, right? What we're saying is in every concrete example anyone has ever come up with where it's calculable, that does not happen. And the numbers are order 1. But maybe someone will come up with a theory like that. And that would be a solution. That would be a solution up to the square root of that factor of the hierarchy problem. It's yet another possible solution. No one has imagined any such thing. Or maybe someone will come up with a theory where the coefficient of the Higgs mass, where the Higgs mass is the first non-trivial counterexample to the solution of this Diophantine equation, right? The first solution to this, the first solution to a certain Diophantine equation, in which case the same thing could happen. These sound crazy, right? But it's not logically impossible. And it's the sort of thing that you would need to do in order to evade the logic that we're talking about here. I'll talk about other things that you could do a little bit later. All right, so the real problem with the hierarchy problem is that it appears to make the Higgs mass squared parameter depend extraordinarily finely on what's going on in the ultraviolet. And in every example we know where it becomes sharp and the Higgs mass is calculable, there is a visible fine-tuning of the parameters that has to be done in order to make it light. OK. And of course, for a long, long time, no one wanted to imagine that there was any kind of tuning going on. And we'll come back to say a little bit more in a second. But something else that I want to quickly say is this idea of naturalness, which is, again, recently getting more of a beating. It is important to remember that this is not the first time that this idea of naturalness has been used and has been successful. In fact, 3 or maybe even 4 times in the last century, exactly this kind of question arose. Exactly this kind of naturalness issue arose, and the logic that there had to be new physics at some scale turned out to be the right answer. Okay? I'll quickly go over some of the examples. I think this is something many, many of you have heard of, but let me just just tell you what the 3 of them are. One of them is the ancient problem of the early 1900s of trying to make sense of the fact that the electron has a finite mass that isn't infinite, despite the fact that the energy in the electric field surrounding the electron is naively infinite. So if you look at the classical energies, the integral of electric field squared around the electron, you get something that's linearly divergent, very much like the hierarchy problem, which is quadratically divergent for the mass squared. Here, for the mass, you get something that's linearly divergent. And if you cut it off at some scale A, some size of the electron or something where you want to say new physics has got to come in by this scale, the logic would tell you that E squared over 4 pi A, which is the energy stored in the electric field up to that point, should be comparable to MC squared. So you get an A, which is E squared over 4 pi MC squared, M electrons C squared. So this was a logic of Abraham and Lorentz and Poincaré and their friends. And what they tried to do was actually build theories where the electron had a finite size of that size. That was the Technicolor of the early 1900s. But then as now, something as dumb as Technicolor wasn't the answer. And it was much more interesting. Actually, the history is very similar. They also had internal theoretical difficulties with this idea, just like Technicolor had tremendous internal theoretical difficulties before it was actually killed by experiment. Okay? And here it's killed by experiment because we now know the right answer. The right answer is that there's electrons and positrons. There's relativity in quantum mechanics, electrons and positrons popping in and out of the vacuum, et cetera, that change this point-like picture of the classical electron. So it wasn't that it had a finite size, but it's interesting that while their model was totally wrong, their logic was spot on. In fact, the scale at which the new physics comes in is the Compton wavelength of the electron and the positron. This is the real scale, A real. And you'll notice that this real scale over their guess scale is actually precisely 1 over the square root of the fine structure constant. So the new physics came in 137 times earlier than it had to. Okay? Their logic was exactly correct. In fact, it was so correct they couldn't have guessed how good it was. It happened 137 times earlier than it had to. Okay, so that's the most famous example. The second example we talked about already. It's the charged pion, neutral pion mass splitting, which once again, you would predict from this logic that there has to be some new physics coming in at some scale. It actually wasn't the lambda, of course, it was the rho. But the rho meson comes in to cut off that quadratic divergence at just the right scale. In fact, once again, it came in a little bit earlier. If you put in the numbers, it had to come in by 1.2 GeV, and actually came in at 770 MeV. And the fact that it came in earlier is, again, a weak coupling factor. So 1 over root n. It's not much of a weak coupling, but it is a parametric fact. If we imagine going to much larger n, then the new physics would have come in, once again, quite a bit earlier than it had to. All right? So that's a second case where it worked. Third case was KK bar mixing, where delta mk over mk was proportional to some G Fermi squared once you get a cutoff squared. And that cutoff had to be less than about 2 GeV, according to Gaillard and Lee, and the cutoff was, of course, the mass of the charm, which indeed came in beneath where it had to, at 2 GeV. Exactly the same. Okay? Power divergent quantity, you make an estimate for the scale, and that's it. Actually, there's another example. It's not quite, it's not of a power divergent quantity, but just to illustrate how often we use this kind of logic and how often it's successful. The very fact that we believe that precision electroweak says that there's a light Higgs. Why do we believe that? We believed it because of the S and the T parameters. Well, every composite Higgs Technicolor model builder knows that all it takes is a few 10% tunings for the S and T parameter to be OK. So what's the big deal? It's only a few percent, right? Oh, well, we're so sure. Oh, give me a break. There's going to be some like accidental 5% accident just so your theories survive. No way in hell, right? And that logic was correct. We discovered the Higgs. Okay? We didn't have this counterexample. There was a little bit of tuning, and it was a little bit crappy like that, right? It was just something very clean and very nice, and exactly what you naively read from the experimental results. So we do this kind of thinking all the time, and it's worked over and over again. This is not something that has just been pulled out of theorists' asses in the last 30 years, even if they're very distinguished asses like those of 't Hooft and Wilson. Okay? This is an idea that has a long history and has worked over and over again. All right. So that's naturalness rah-rah. But the problem, as you all know, is that there's been also, from the very beginning, some tension with the idea of naturalness. Something seems different about this incantation, this incarnation of these questions than the times before where naturalness has been so successful. And it's not just that the LHC hasn't seen superpartners or any new sign of physics yet. It goes back right to the very beginning of this subject in the late 1970s and early 80s, which is that there was already a tension from the fact that if we believe there's lots of new physics at the weak scale, we might have expected all sorts of higher dimension operators that violate the approximate symmetries of the standard model that no longer have any good reason to be true if we have new physics around the corner, and we didn't see any of them. Okay, so that was true right away, right from day one. This is why the subject of beyond the standard model physics existed, and theorists had something to do. Okay, it's because you had to do something. The people didn't think of it as a disaster for the idea of naturalness. They thought of it the other way around, as an opportunity, not a problem. An opportunity to discover some special structure of the new physics at the TeV scale that would solve the hierarchy problem and not give you huge flavor change neutral currents, huge baryon and lepton number violation, large EDMs, and so on. Okay? But the fact that as the 80s turned into the 90s, turned into the 2000s, that we continued not to see any signs of indirect new physics, together with the fact that we didn't see the new particles directly at accelerators, is what's ratcheting up the tension on this idea of naturalness. What we know now, I think there's probably loopholes even to this argument, but it doesn't look like this. It doesn't look like these earlier cases where naturalness worked in a big way. Nobody was sitting around. There were no conferences. There were no talks with people sitting around back then with experimentalists having probed the structure of the electron down to 10 to the minus 14 centimeters. No one was saying, well, is it okay if the electric field energy is 20 times bigger than the bare mass and there's a 5% cancellation? Maybe that's okay. How do you feel about that? No one was talking about their feelings, okay? Which is very good. We do very bad in our field when we talk about our feelings too much. So when naturalness worked, it works in a big, big way. And that's not the case now. The analog to that would have been discovering stops, not even at 400 or 500 GeV, this estimate that was erased up there. That is not natural stops. That's natural by our pathetic standards today. Okay? What would have really been natural, what would have looked just like that, would have been stops, right around the mass of the top. Right? This is a theory of the weak scale, after all. It's crazy that we're starting to talk about 2 TeV particles, even 500, 600 GeV particles, to explain where the numbers 80 and 90 GeV come from. Okay? That may be the way things are, but that's not like that. There was no arguing back then. That's because when the theory has weak coupling parameters, the corrections to the quantities should be small. They shouldn't be comparable to the quantity that you're talking about. They should be small. They were small then. The standard model is perturbative. Of course, the top Yukawa coupling is bigger than alpha, but it's still a relatively perturbative coupling. The alpha top is like a 1/10. So maybe a little bit bigger, but there's no reason to have things. If it had worked like before, we should have seen the particles directly before. This is true of every extension of the standard model, not just supersymmetry. Supersymmetry is a particularly good example because everything is so constrained and calculable, you can see what the problem is in front of your face. People talk about fine-tuning in simple supersymmetric theories at the sort of few percent, 1% level, but the problem is really more parametric than that. It isn't that there is tuning for electroweak symmetry breaking. There is, but the sort of bigger problem is that superpartners should have shown up not at the LHC, but at LEP. They maybe even should have shown up at Petra. And that's because it's a theory of the weak scale. You would expect in supersymmetric spectra, you expect colored particles to be heavier than uncolored ones. But because the Higgs talks to the top quark, which is the biggest coupling of all in the standard model, we expect the Higgs to be up where the stops are, with the colored particles, and the Higgs mass squared sets the weak scale. So we would naively expect that the Z and the W and the Higgses and the stops and squarks and gluinos to be hundreds of GeV, and the sleptons and the electroweakinos to be lighter than that. And this is why very serious, sober theorists in the late 80s and early 90s were writing papers with superpartners discovered at LEP. They weren't the people that we won't talk about here who've been saying for 20 years that supersymmetry is 6 months around the corner as a time translational invariant statement. Not those people, okay? Other people, much more reasonable people, who really thought that supersymmetry should have been seen at LEP. It was a totally reasonable argument. And actually those people started saying there's something wrong pretty quickly after that. So they've been very consistent, okay? They've been very consistent. Not something dramatically wrong, maybe. Maybe it's all still fine, but it's the beginning of a divergence in the road from that case and the previous cases where the idea of naturalness has worked. Okay, so that's the so having said all of that, even allowing it to creep into your head that there might be something wrong with the idea of naturalness. What could it be? Can we go back? But we just saw that historically naturalness has always worked, right? Well, that's not true. Anyone who studies their history of science knows that you can come up with examples to illustrate any polemical point you want to make. And there are very good examples of situations where naturalness has failed very dramatically as well. There's a kind of an ancient one, which is so ancient that I don't want to spend too much time talking about it because it might not be so relevant to our situation today. But the ancient Greeks, Aristarchus in particular, had a wonderful heliocentric model of the solar system, exactly the one we have today. And his colleagues rejected it because Aristarchus himself brilliantly worked out the distance from the Earth to the Sun, which was already a gigantic, huge number to everyone back then. But then he realized that if it was heliocentric, you had to see parallax of the distant stars. And we know parallax is just too small to be seen by the human eye. So people didn't see parallax, and they said, oh, really? So if your model is right, and the Earth goes around the sun, not only is the Earth so far away from the sun, but all that other stuff out there is vastly further away, even than that. Yeah, right. That's lucky for you, isn't it? You know, just put them just far enough away that you don't see them, right? That was right. That was right. They couldn't know. They didn't know about gravity. They didn't understand the dynamics. They didn't understand any of that. It badly conflicted with the notion of naturalness. That's why Tycho Brahe actually had an intermediate model for the solar system that had fewer epicycles, was better than Copernicus's in many ways, where everything went around the sun, but the sun went around the Earth. Not because he wanted to put this Earth at the center of everything, none of that crap. These people were very smart pragmatists. It's because he didn't want to have the parallax problem. And today we know there is a parallax problem. Those stars really are really far away, and it's because of gravity and dynamics and clumping and the history of the universe and how the solar system formed and all the rest of it that they couldn't possibly have any idea about. Okay? So that's one example where people's notion of naturalness was very badly wrong. Of course, much closer to home, we have Raman's favorite Greek letter. Okay? We have the cosmological constant problem, which is just a crushing weight on the idea of naturalness. Right? You know, so exactly the same logic for the hierarchy problem. In the case of the cosmological constant, predicts new physics at the millimeter scale, and we can all do the experiment that shows there isn't any new physics at the millimeter scale, with apologies to Raman. So doesn't that already tell us we're completely full of shit when it comes to thinking about the hierarchy problem? Maybe it does, right? But again, we don't know. That's not quite the way the history went, but you could imagine a relatively sophisticated theorist of the early 1900s, right around the time people were worrying about the self-energy of the electron problem, saying, you guys are wasting your time thinking about that stupid problem. There's this much bigger cosmological constant problem. Probably what solves the cosmological constant will solve that problem too. It's complete garbage, right? Not all problems are solved in the same way, and it's never a good idea, especially in theoretical physics, in any part of physics, especially in theoretical physics, to take an overly mystical attitude towards things and say, oh, something is going to come. Well, that's something, we have to find it. You have to get concrete as soon as you possibly can, and not just sit out in the fog forever, okay? So the people who went ahead pragmatically and tried to solve the problem solved it, and they were right, despite the fact there was a CC problem sitting there. The charged pion, neutral pion mass splitting problem. It sounded ridiculous, but you could have said exactly the same thing. How can I trust this power divergence when I don't understand the other one? That's a really stupid thing to do. That there is a nice rho meson, you're going to see it, and it's there, and so on. So the fact that this is sitting there does not necessarily mean that there won't be a solution to the hierarchy problem, but it makes you wonder about it. Okay? There is something else. There are a number of other smaller things. If we go down one energy scale from the weak scale to the scale of nuclear physics, nuclear physics is a fine-tuned theory for no apparent reason that we understand. For example, this is what makes nuclear physics difficult to learn. For instance, two neutrons are not bound. A neutron and a proton is bound, and the deuteron has a relatively small binding energy, 2 MeV. 2 MeV is much smaller than nuclear physics scales. That's about a 20% tuning. Okay? We don't know why. I mean, it's if you change the up and down quark masses, you change things, you'll change that. Okay? So it's a bit of an accident that the deuteron is so shallowly bound. This is a little more striking. Two neutrons are not bound, but the amount they're not bound by is 60 keV. So this is, it's a very significant fact about the nuclear spectrum, and it's another accident. Looks like on the face of it around a 1% accident that this is the case. And in a more technical sense, if you write down the few nucleon an effective theory that governs nucleons at low energies, as Kaplan, Savage, and Wise did in the late 90s, that theory has two 4 Fermi operators in it, basically the isotriplet and the isosinglet interactions between the nucleons, and both of those 4 Fermi operators are fine-tuned to be close to an unstable ultraviolet fixed point. Okay? There's sort of some amount of tunings of all of them, if you take the product of the two, depending on how you think about it, is between 1% and around 10 to the minus 3. Roughly speaking, it's these two guys, the smallness of the deuteron binding energies and the largeness of the nucleon scattering length, which is the inverse way of talking about that small anti-binding, non-binding. All right, so we get so exercised about percent level tunings, we go down one energy scale, and nuclear physics has these percent level tunings just in it. And no one is going around saying there's a crisis in our understanding of nuclear physics. Okay? Now, interestingly, these tunings are definitely related to the weak scale. because it's the up and down quark mass. This is not purely a property of QCD. It's also controlled in an important way by the up and down quark masses. So it's a little bit interesting that the tunings that we see are related to something else where we're starting to have some concerns about the idea of tuning, namely electroweak symmetry breaking quantities. There's another famous example, the low power of the quadrupole in the CMB. That was a case 20 years ago when theorists made a prediction for the size of delta rho over rho that was a lot bigger than what experimentalists ended up seeing. And as in that decade when the experimentalists were looking for it, the theorists kept updating their predictions to make it smaller and smaller. You could cynically say they're running away from the experiments. Aha, you're running out completely. No, but it was seen at the 11th hour. It was seen at 10 to the minus 5. And the reason it was so low, as far as we have this famous low power of the at low L in the CMB, and just naively, it's about a few percent accident. Okay? So these, and the final few percent accident is that the moon eclipses the sun almost perfectly. That's about a few percent accident. Okay? That doesn't have any deep significance. And by the way, it's a time-dependent statement. When the dinosaurs were wandering near the Earth, it wasn't remotely, the moon was twice as big in the sky. It wasn't even true, right? So there's a look elsewhere effect. But there is a time at which it's true, and it's interesting that we live in that time. Anyway, so we've seen there is a huge thing, the cosmological constant, and there are scores of little things, niggling things, that suggest that naturalness has definitely failed in the past. Now, naturalness failing means something specific. Naturalness, in this case, is making a prediction for where new physics is based on the size of the low energy power divergent, an estimate of the size of low energy power divergent corrections to the quantity of interest. Okay, so that's the idea. I don't know whether it really means there's tuning in the ultraviolet or something else, but just the pragmatic aspect that you make a prediction for where new physics is, and that failed badly for the cosmological constant. And we also have these other examples where percentage accidents seem to happen, even though we don't have any very good reasons for it. All right, so, yes?
The CCF code, all your examples are always tuning of a percent.
Exactly, yes, yes.
Are you saying that, does this motivate you to think that even if you don't see it at the LHC, the solution is right around the corner?
Well, I will come to this in a sense. I want to insist on talking about invariant quantities, okay? So I don't want to say I think 1% is fine and 10 to the minus 4 is bad. That's what I feel. But there's something invariant, which is if we're missing the new physics because it's percent tuned, like these times it's happened before, it's possible we'll miss the new physics at the LHC. We will not miss it at 100 TeV proton-proton collider, okay? So we'll just not miss it, if it's like before. On the other hand, if we continue to see nothing at 100 TeV proton-proton collider, then the fine-tuning is 100 times worse than anything we've ever seen before. Okay? That is an invariant statement. Now you can say, does that make you excited, not excited, do you care, don't you care, that's about you. But as an invariant statement of what would completely nail this if we don't see the new physics at the LHC, the obvious thing to do is to keep going to as high energy as you can at a PP collider. And what it would do if you continue to see nothing is take the tuning to the 10 to the minus 4 level, which whatever else you think, as I said, the invariant statement is it's 100 times worse than any tuning we've seen anywhere else other than the CC. Okay, so it would start taking the Higgs from the sort of, from one extreme we all thought 20 years ago, which would be totally natural, through this never intermediate land where it may be as crappy as other things we've seen, out to, quite in the clear, much worse than anything we've seen before, and heading in the direction, of course, of the truly horrid thing associated with the tuning for the CC. All right.
Can I say something about it?
Yes.
About whether we want to go for 80 TeV, I'm all for it, so it's nothing to do with that statement. I just wanted to make a comment. I'm still thinking about the G mechanism and the charm, okay? So suppose that the charm was at 3 GeV and not at 2 GeV.
Yes.
I mean, the thing that was hard there is that the G paper is 9070, and you didn't have asymptotic freedom yet. So you didn't even know about the J size. So if you would conclude that you need to go to 50 GeV machine, you might lose this neo resonance. So things could be also elusive. So you need maybe precision versus just
That's maybe not a good example for. Well, we can talk about that. We can talk about the example. I disagree with I disagree with what you said, but maybe we can. I disagree with what you said for this particular example. Maybe we could talk about that later. Yeah, right.
Could be also a factor.
It could, yeah. By the way, I mean, well, this is not the time for that conversation. But if you have a 100-kilometer tunnel, you also run the E+E- mode, and that's just awesome. Okay, that's really awesome. For this purpose, it's really awesome, especially when you go back to the Z. You can get a factor of 1 million more Z's than we made at LEP, and that gives you a second handle on precision electroweak operators. Yeah.
The ISAB did not find the observed size simply because that any detector was the same, which was
yes.
15 degrees from the
Yes. So we don't just want to collide two protons in the middle of outer space with nothing around them at 100 TeV. But anyway, I agree with you. All right. So sorry. So but I want to get to some more substantive things. So what are the options? So what are the options for what we might see? So obviously, it could still be natural. And it really could still be natural. It could be natural in the Raman formula sense. Maybe in lots of simplified models with stops decaying directly down to the bottom of the spectrum have ruled out stops above maybe almost 600 GeV now. So that's getting you into 10% territory. But I don't think enough simplified models, even with like Higgs-Zenos in the middle, have been looked at and so on. So I think it's possible. It's possible that there are still some squeeze regions and other regions where officially, according to this, according to the 400 or 500 GeV colored particles measure, things are still natural. This is it's perfectly possible. It's quite natural, and I think it's also perfectly possible, as we've seen in these examples before, it could even be percentage tuned. The problem with percentage tuned is that now we're on a slippery slope, right? We've in mixed company, we shouldn't say it, but we've decided what kind of person we are, and now we're haggling over the price, right? So and that means that we might see it and we might not. Percentage tuned could mean 2 TeV stops, everything else heavier than that, and then we'll just miss everything at the LHC. Okay, we could still see things. So but the people were very happy about the LHC in the aftermath of the cancellation of the SSC, partially because there was also a time in the early 90s when the conventional supersymmetric picture looked as good as it has ever looked. Few hundred GeV superpartners, colored particles, and so on was totally reasonable. But if you really want to be sure, even covering these percentage-tuned regions, if not more, you want higher energies, and that's just life. The SSC would have been awesome. We should have discovered the Higgs in Waxahachie in 1999, but there's not much we can do about that now. But I should say, just now I'm doing what I said I shouldn't do and talking about my feelings, but I think this is totally plausible, and it wouldn't shock me. I'd be disappointed just for my own life, but we'd still learn something about nature, and that would be great. All right, it could be unnatural. And now what I mean by unnatural now has unnatural sharply means there's no new physics associated with solving the hierarchy problem anyway. And this divides into two things. One of them is the multiverse anthropic set and line of thinking. And I'm dividing this up in this way for a reason that should become apparent. And the other one is what I derided earlier as something else. We're just so stupid. We're just thinking about everything wrong. We're just dumb. And there's something about this physics we just don't understand. All right. And in this something else, this divides up. I ran out of space. Divides up into there are things that are just too dumb for even words to talk about, like use dim reg. Okay, so let's not even talk about that. There are slightly less dumb ideas, which have been around and people have thought about for 20, 30 years, like the standard model becomes conformal. Okay, this is another slightly dumb idea. Okay, we'll talk about that a little bit. And then there are things which are, I think, more along the lines of what people have in mind when they say something else, which are just we're missing something much more radical in our thinking about these problems. And here is where I just want to spend a few minutes telling you about a few of these entries from my notebooks. Not all of them, but there's a few lines that I want to mention here, because interestingly, many of them have low energy consequences. Many of them have consequences for physics that does not involve the usual things that we look for. None of them work, by the way, so you shouldn't get too excited. But just as inspiration for the sort of thing it might be, just to see that they're not all completely sterile. They have consequences. In fact, the things that kill them they make so many predictions for low energy physics that they're false already. Okay, all right. Okay, but now I should also say something. These two pictures, let's say we see the Higgs and nothing else. These two pictures are, of course, operationally identical. In both cases, we've seen no new physics, right? But this is just always a more concrete and a more pragmatic approach than just saying nothing, right? This is at least a picture for what might be going on. Maybe that picture is also wrong, but again, it's always better to do something than nothing, which is what most of the belly aching here is about. So let me say a few things about this. First, before saying the word multiverse or anthropic, let me just tell you an interesting fact about our two parameters of the standard model that are fine-tuned. We have the cosmological constant, and we have the Higgs mass squared parameter. Okay? These are the two tremendously fine-tuned quantities. And they have some values down here in natural units, Planck units, whatever they are, 10 to the minus 32, 10 to the minus 120. Okay? So this is the observed place where they are. So, we're here somewhere. Now we can do an exercise. We can ask in our mind's eye, because we know so much about physics, we can see what the world would look like if these things were more natural. So what would have happened if the cosmological constant was bigger, which is what would make it more natural? Or if the Higgs VEV was bigger? I mean, I literally say, take those two parameters in the standard model and let them become more natural. What would happen? What would the world look like? And here there are these famous statements, the most famous being Weinberg's argument that if you make the cosmological constant even 10 times bigger than what it is, all of a sudden up here, above this place, not far from where we are, the universe is empty. Okay? It's rather striking that something so quickly happens as I make the cosmological constant a little bit bigger. The universe is empty. And as you make the Higgs VEV a little bit bigger, what happens even within a factor of 3, so 3 times 10 to the minus 32, is something else happens. There's no atoms. No atoms plural. No atoms other than hydrogen. That's because as you make the Higgs VEV bigger, the down quark gets even more massive than the up quark. And at some point, the neutron-proton mass difference exceeds the nuclear binding energies. I mean, again, if you're a beginning student, you think, why do we have nuclei? The neutron decays, right? The neutron decays in 15 minutes. So why do we have nuclei? Well, it's because nuclear binding energies are bigger than the neutron-proton mass splitting. But they're not the same thing. Those two quantities have nothing to do with each other. It's a complete accident in the standard model that they're close, so that we can have complicated nuclei and therefore have complicated atoms, plural. If we didn't have that, it would just be hydrogen. In fact, if it goes a little further, the down quark becomes so much heavier that the delta becomes the lightest of all baryons. And then the atoms are all helium, okay? Functionally helium. But anyway, the fact that it's just that we have atoms fails, okay? All right, this is just a fact. It's just a fact. We can do this exercise, and the result of this exercise is these two things, right? Now, if you have a conventional picture of the world that many people had for a long time, there's a unique underlying theory that uniquely predicts all the parameters of the standard model and everything else, then every single dimensionless number in nature is the answer to some formula, right? So it's coming from some computation, maybe like that, or some other ones. It's given in terms of pi's, e's, √2, the golden ratio, whatever the heck they are. Okay, but you put these dimensionless numbers together, and you get the answer for every single number, including these. And then you have to believe that, oh, look at that, amazing. Absolutely amazing that these pure numbers conspired to give us just those parameters we needed so the universe isn't empty and it has complicated enough atoms so that we have interesting chemistry and so on. Okay? I'm not saying it's false, although from my tone of voice you can perhaps guess that I find it personally very implausible. Okay? But that's what you have to believe. On the other hand, you see that this picture isn't just saying throw everything out, we can explain everything. You know, it's taking some inspiration from this fact. This is a very remarkable fact about moving these parameters around, and if you believed that there was a gigantic multiverse with zillions of vacua which are populated somehow, then, and that there are so many of them that we could accidentally find regions where the cosmological constant was small and the Higgs mass squared was small, then you would believe, following Weinberg and Donahue and friends, who made these two arguments, that we should be close to a corner like that. Okay? That there's no reason, that there's a reason to tune in those regions of the multiverse where that didn't happen. It's empty, and perhaps less dramatically, there's no atoms. So you should just tune just enough to find yourself close to these dangerous borders where physics changes so radically. In other words, if the cosmological constant was 1 trillion times smaller than that even, then this wouldn't be the explanation for why it's so small. You'd have to find some other explanation to make it 1 trillion times smaller. That was the way Weinberg wrote his paper, by the way. He wrote it as a way of falsifying anthropic reasoning, to say that it makes a prediction that we should see a cosmological constant in the next round of experiments. If we don't, these ideas are starting to be falsified, and of course we did, okay, at basically the size that needed to be there. Okay, so this is some circumstantial evidence for taking this kind of picture seriously. It's not remotely a science yet. That's the other thing about this. You know, even the theoretical structure for how to make sense of eternal inflation and understand all these vacua and so on, it's not close to the point where we can where we understand it theoretically well enough to be able to make predictions. But you know, if we understood everything about physics all the time, we would do something else with our lives. There's an important set of theoretical questions to explore here, and it could be that we're going to start getting more circumstantial evidence for taking it seriously, not for it directly, but for taking it seriously from experiments. I just want to make 2 comments about a landscape before moving on. One of them is that, you see, if you believe there's just one underlying vacuum, then the principle of naturalness could never actually be a real principle of science. The principle of naturalness would be a sort of a guiding, would guide you for the sorts of new physics that you might imagine. Right? You might imagine new physics which allowed large scales to be generated in a natural way. But if there was one underlying theory, then in fact there is no way of adjusting the parameters. Okay? One underlying theory is one underlying laws. There is no way of adjusting the parameters, and so, you know, naturalness is just a guide for guessing what good new theories are, which is perfectly fine, right? But it couldn't by itself be a sharp scientific principle. In the context of having an enormous landscape of vacua, naturalness becomes a well-defined question. Because now, especially if there's so many of them that we effectively get to continuously imagine vacua where the parameters change, now they really are all out there. They're really all out there as potential solutions of the underlying theory, whatever it is. And now it becomes a serious question, why we have this one and not that one. And whether or not the way people are attempting to address these points involving trying to come up with a notion of a measure on the state of on all the vacua and so on, maybe whether or not that approach is the correct one or more radical reinterpretation of this picture is needed. Regardless of that, having these exponentially large number of vacua makes it possible to find vacua that have small enough lambda and Higgs mass, perhaps. So it's at least, you know, concretely possible to find vacua like that. And the question of trying to understand the measure on these set of vacua sharpens and makes the naturalness issue something that's actually scientific. So it's ironic that naturalness really becomes not just a guideline, but a more concrete, turns into a more concrete set of questions if you believe there is a huge landscape that actually allows you to sample these different values of the couplings. The other thing I want to say is that it doesn't have to be the case that we have to understand all of these issues about the measures in order to be led to a prediction about what the long-distance world looks like. Something which people have always said, and we just said earlier today in the context of these tuning problems, is that the cosmological constant problem is so huge, what if it just trumps everything else? You know, it trumps everything else. How dare we think about this 30 orders of magnitude problem where we have a 120 order magnitude problem? But I at least never had a concrete picture where that trumpage was concretely realized. But you might imagine a picture like that in the context of a landscape. Let me give you a simple example. Suppose you're done. We understand everything about the theory of everything, all the vacua that there are, and we count and we count and we count, and we find that here's a region where SUSY is broken at the 100 GeV scale. Just what it should be in order for things to be natural. Everything is awesome. If you're a particle physicist, you're thrilled. The Higgs mass is naturally small. Everything is perfect in this vacuum. But let's say you count and you find 10 to the 60 vacua there. Let me pick a better example. 10 to the 30 vacua there, right? Tough luck. It's perfect from the point of view of a particle physicist, but there just aren't enough vacua to make a small enough cosmological constant, right? So it has nothing to do with measures. It has nothing to do with that. It's just there isn't even one, right? And you might be forced. You just might be forced to go to somewhere where now the SUSY breaking scale is 10 to the 5 TeV. I don't know what it is, but it's much higher. Here you have to fine tune in order to find a light Higgs. Okay? But here there's 10 to the 200 vacua. Plenty in order to find one that makes the CC small and the SUSY breaking scale small. So what I'm saying is that it doesn't even have to permanently be lost in issues about measures. It could just be a case of finding one. If the landscape looks something like this, if we understood it from the top down, we could make incredibly sharp predictions about what the long-distance world looks like, simply by finding the first place where it's possible to find one vacuum that looks like ours. Okay? All right. So the final thing I want to say about this picture of the world is that it suggests that you can't build random theories like this. Okay? Of course, the most obvious theory of this sort would just be the standard model and nothing else up to humongous energy scales, right? So just swallow the 1 part in 10 to the 30 tuning. Now, I personally find that relatively implausible for many, many reasons, but again, that's my personal feelings. But there are other things that are much milder that it could be. It could be the minimal version of split SUSY, with the scales of supersymmetry up at hundreds or thousands of TeV. The fermions in the TeV scale, unification works, dark matter works, and so on. So that's something else it could be. But one thing that you cannot have, you see, you can't do anything in this picture. If you're taking the anthropic motivation, you can't have random effective theory at the hundreds of GeV scale. The only scalars that are light should be the Higgs, because it costs tuning to make the Higgs light, and the tuning has a purpose in life. You see, so the only fine tunings that you're allowed to have in that picture of the world is one which has a significant impact on the long distance universe, a big impact on the long distance universe.
What about something like baryogenesis through those extra scales?
Well, so we could talk about that. We could talk more, but that actually becomes and in fact, you know, there's a very well defined rule for anthropic model building along these lines. Those rules were pretty well articulated, I think, in a paper I wrote with Savas and Shamat Kachru, where we actually built models like this. Okay, where in fact, as you said, we built models where with some underlying idea for what the parameters that are being scanned looks like, you have to tune additional scalars to be light in order to do something. But in all cases, it's not just a scalar that comes down. The scalar comes down with some other set of stuff that you can eventually identify as doing this important thing. So some fermions came down as well. So you had an additional singlet and fermions to get a phase, to get a more strongly first order phase transition, blah, 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 blah. Okay? But it can't just be random things coming down with no discernible reason whatsoever. Okay? So whatever comes down, whatever is tuned to be light, you have to be able to identify something terrible that would happen to the world if it wasn't tuned to be if it wasn't tuned to be light. So there are ways of really falsifying this picture, or at least making it much, much less plausible. Just to give a simple example, let's say we discover a second Higgs. Let's say, we in addition to the Higgs, we discover a second doublet at 600 GeV, and that's it. That's everything we discover at the LHC. Okay? Well, that second Higgs has zero purpose in life. Okay? In fact, it has so little purpose in life, we didn't know anything about it until we built this big fancy machine to make it, right? And not even indirectly. We just needed one of them to drive electroweak symmetry breaking. Having a second one is totally pointless. But let me give a little caveat even to that. It could be that in the underlying theory, that Higgs and our Higgs are actually part of a multiplet together. Okay? So maybe they're part of a multiplet that rotates them into each other. Maybe there's an SU2 symmetry that could rotate that Higgs and our Higgs into each other. Okay? That would mean that one tuning in the underlying theory is all it takes to bring both scalars down. And of course, that symmetry's got to be a little bit broken, otherwise they would be identical, right? But if that picture is correct, there's a very sharp prediction, which is that all the large couplings of the second Higgs should be identical to the large couplings of our Higgs. Gage couplings are the same, but the important part would be the coupling to the top. If it's going to be a part of an SU2, the coupling of the second Higgs to the bottom has got to be exactly equal to the top Yukawa coupling. Okay? So if you saw that, if you make a second Higgs and you see that its production rate I mean, in a standard 2 Higgs doublet language, this would be a very large tan beta of 60 or something like that. But you would have to eventually be able to measure it and see that it's exactly the same as the top Yukawa coupling. If it's even 10%, 20% different, then we couldn't possibly explain it in this anthropic sense. But if it is exactly the same, then it's conceivable they're actually both being tuned down together. Okay, so it is an example. This set of theories is a tiny subset of all the possible random theories you could have, unnatural theories you could have at the weak scale. Okay? And that's also what I said. It's all somewhat more pragmatic. It's associated with a picture for what might be going on, and that picture leads you not to throw everything out, but to consider a limited set of theories for what might be going on. Because of the paucity of scalars, and getting only new fermions, essentially, are the kinds of particles that you would expect to discover in this kind of picture, as in split SUSY, which I still think is the sort of best representative of this idea that isn't just the standard model, you would expect long-lived displaced decays, just as a very generic feature. And the reason is if you have new fermions, it is hard for new fermions, especially it's impossible for new colored fermions in the adjoint representation, but hard in general for new fermions to decay to standard model states through normalizable interactions. They have to decay through higher dimension operators. So that's very exciting, because if you produce the new fermions and they decay inside the detector at all, then you've seen direct evidence for a new scale at the hundreds or thousands of TeV scale, right? It would be extraordinary to finally have, once again in particle physics, a higher dimension operator, right? As we did when we saw the weak interactions that told us where the next scale was and where to go. And also, if we see that, we'll have much, it's somewhat circumstantial, but we'll have evidence for vastly more tuning than if we see the Higgs and nothing else. Because not only would we just see the Higgs, but we'd also see evidence for another high scale, much, much higher than the TeV scale, and a big desert up to there which gives rise to these, which gives rise to the decay. So that would put at least indirectly evidence for tuning into the part in a 10,000, 100,000, part in a million level. Okay? So there are things that will never get direct evidence until we understand better how to think about this whole multiverse. We'll never get direct evidence that there are all these other universes and all the rest of it, and we may even be thinking about it and talking about it wrong. But what we could get direct evidence for is an indication of where the next, the scale of next new physics is, and absent that, an indication of a level of fine-tuning, which is something that we can quantify. So if the LHC sees the Higgs and nothing else, we'll have evidence for fine-tuning at the percent level. If 100 TV collider sees the Higgs and nothing else, as we said, we'll have evidence for fine-tuning at the 10 to the minus 4 level. Of course, in all cases, both the LHC and obviously a future accelerator could also see lots of new physics. Okay, so that's it about this direction. And if I can take 5 minutes, I want to tell you about some of these guys. But maybe, when did I start? I've gone 15 minutes over already? Okay. Actually, so perhaps what I'll do is this. Maybe I'll just say just a few tiny words about these, and anyone who wants to know about these lines, I can tell you more about it privately. Oh, really?
I can imagine working on the lines that you just were too dumb to figure out.
Right.
But I can't ever imagine working on dim reg or standard model going into performance.
All right. Okay. So do you mind if I talk for just a few minutes about that? Okay. Fine. All right. So maybe I can just tell you about. Okay. Maybe I won't tell you about even as many as I was planning on, but let me tell you about the two most interesting ones. Okay, one of them is just one set of words. Every grad student theorist who's thought about these problems has said these words. So I'll just even put this up very, very quickly. This is more a comment for maybe some of our Nets Matter colleagues or other people. But there are other situations in nature where we see things that look like one way of talking about the hierarchy problem is why the weak scale is so close to a phase transition, to the electroweak phase transition, relative to the underlying scale of short distance physics at the Planck scale. And there are analogous situations where a system brings itself very close to a phase transition without any new physics, without in a way that doesn't conform to our ordinary notions of naturalness, but it's such a different situation that it's hard to know what lesson to extract from it. Anyway, the general phenomenon is known as self-organized criticality, and it's something that many of you have seen if you go to the beach and you see sand dunes. You'll notice it's actually pretty striking if there's enough dunes. So you see lots and lots of them in a big line. You'll notice that the angles of all the dunes are almost exactly the same. Okay, you don't find dunes, some shallow, some they're all basically at exactly the same angle. And people have done these experiments for years and years where they make sand piles. They drop sand, and they start growing a pile. So first it's like that, then the pile gets bigger and it gets steeper and steeper. But it always reaches the same angle eventually. And it reaches the angle such that when you add one more drop of sand, it triggers a little avalanche, and it brings it back to the original angle. Okay? So that's a situation where if you knew nothing else, you just looked at it, you'd say, look how crazy that is. It's so close to the place where if I just add one more drop of sand, it triggers an avalanche. Why is it so close to the avalanche phase transition? Right? And yet, that's why it got there to begin with. Okay? So now, all of us who have tried, certainly me, I can't tell you the number of months of my life that I've spent trying to make analogs of this in relativistic quantum field theory, and I fail over and over again. And there's no reason to go through the technical failure in all the cases here. But perhaps some 20-year-old in the audience will find a good way of thinking about this. But a more interesting example, a more concrete example, is a not very well-known paper. It goes back to a not very well-known paper by Ed Witten in '95. This is a fantastic, this is an incredible idea. This is one of the most, exciting word-level ideas for solving the cosmological constant and hierarchy problems that I'd ever seen. And as you'll see in a second, it also spectacularly fails. Okay? But it spectacularly fails because it makes an infinite number of predictions about low-energy physics, all of which are wrong. Okay? But it opens up, well, so let me just talk about it a little bit. How many of you know this paper? Okay. Leave the room, Matt. All right, so Witten's idea is that SUSY is not broken. Okay. By the way, I suspect I'm much more enthusiastic about this idea than Witten himself. Okay, there was a throwaway paper for him, but I think it's more evocative than he does. So his idea is that SUSY is not broken, and not that it's broken by, it's just unbroken. Nature is supersymmetric. Our nature is supersymmetric. Okay. Now, how could that possibly be? Well, so he took inspiration from. So we normally say that that unbroken SUSY equals Bose-Fermi degeneracy. And we haven't seen any of the superpartners. Okay? But he began by pointing out that unbroken supersymmetry does not actually imply Bose-Fermi degeneracy. And at least in 3 dimensions, it doesn't. So if you're in 3 dimensions, there's a peculiarity of physics in 3 dimensions that's related to the fact in Newtonian gravity that you get logarithmic gravitational potentials and not 1/r potentials. So that even if you have a point mass, see if we have a point mass in 3 dimensions, then the gravitational field dies off at long distances and we just have flat space. But in 2 dimensions of space, 2 + 1 dimensions, any point mass actually has a significant back reaction on the geometry of space-time. And it makes the geometry look like a cone. Okay? With the singularity, the curvature singularity associated with that point mass being just the tip of the cone. And this, the deficit angle, 1 minus the 2 pi minus the opening angle of the cone is just the Newton constant, the 3-dimensional Newton constant that has units of 1/mass times the mass of the particle. So of course, if the particles are small, are light compared to the 3-dimensional Planck scale, this is a minuscule effect, but it's still there. So it's saying that, so first of all, this changes the geometry. And as a consequence of that, while we can say that a supercharge annihilates the vacuum so that the vacuum is supersymmetric, we cannot conclude that a supercharge acts on a boson to give us a fermion state. And that's because that boson, this whole argument assumes that Minkowski asymptotics. And when you don't have Minkowski asymptotics, the argument breaks down. And in fact, you can explicitly take supersymmetric models and calculate the Bose-Fermi mass splitting. And it's supersymmetric, but bosons and fermions don't have the same mass. Very good. Okay, but you say, who cares? We don't live in 2 + 1 dimensions. At least for once, the string theorists aren't going up in dimension, but we don't live down in dimension either. We don't live in 2 + 1 dimensions. Nor are these effects would be absolutely minuscule and tiny, right? But now came the interesting thought. Let's crank up the coupling constant. Okay, you could imagine there is an underlying dimensionless coupling constant that you're cranking up, or that you crank down the Newton constant, however you like. Let's crank up the coupling constant. What happens for a while is that the Bose-Fermi splitting becomes bigger and bigger, right? And then maybe the coupling constant becomes of order 1. We don't know what goes on anymore. But you might still think, so what? But this was right around the time that Edward discovered that in string theory, at least, in supersymmetric string theories, when you make the coupling constant in the 10-dimensional string theory large, you grow an 11th dimension. Okay, and the size of the 11th dimension is actually the strength of that coupling constant. So now you start seeing what the idea is, right? The idea is that we're going to make the coupling constant stronger and stronger. This 3-dimensional descriptions, the bosons and fermions are split more and more. we're going to make it even bigger than that. So presumably they're going to get tremendously split, right? But what's going to happen is that there will be a weakly coupled description of the physics, which is 4-dimensional. Okay? We grow an extra dimension. And so we have a 4-dimensional description of the physics with huge Bose-Fermi splittings, despite the fact that it's an underlying supersymmetric theory. Okay? So it's supersymmetric. The 4-dimensional description will look totally non-supersymmetric, huge Bose-Fermi splittings. In that 4-dimensional description, it will look utterly miraculous if the cosmological constant is 0. Okay? It would take tremendous cancellations that you can't remotely understand. But there's another dual description of the physics, which is strongly coupled. It's useless for every question about what the particles look like and the interactions look like. It's this underlying 3-dimensional picture. But it makes one thing obvious. The vacuum energy is 0. Okay? So that's a kind of a use of duality, which was the wonderful idea, the thing that got me and many other people so excited when we saw this paper. That looks like a brilliant use of duality. You have two descriptions of physics, one weakly coupled, one strongly coupled. Could it be that the weakly coupled description is good for seeing the particle content and all the rest of it, but leaves certain things mysterious, like why the vacuum energy is small, and why the cosmological constant, and why the Higgs mass is small? And there's a dual description, which is useless for everything else, but completely explains where those huge hierarchies come from. So, okay, so that's the qualitative idea, right? Now that as an idea is great. And you might think there's no way we could make more progress on it without identifying such a theory and seeing what it did at strong coupling and so on. But that's not true. We can rule this idea out right away. The reason is it makes many predictions, you see. It's not just that the vacuum energy should be 0. As this coupling gets larger, the circle is getting bigger and bigger, and the vacuum energy at every value of the radius should be 0. Which means not just the cosmological constant is 0, but the entire radius dependence of the cosmological constant is 0. The radius dependence of the vacuum energy is known as the Casimir energy. So not just the cosmological constant is 0, but the Casimir energy's got to be 0 as well. The Casimir energy is something we can calculate just knowing the low energy particle content of the standard model. Okay? And if you just put in the particle content we know and love, which is photons and gravitons as the only massless particles at huge distances, the Casimir energy isn't 0. Okay? So that already tells us that it can't just be the standard model. Now, you can say, well, maybe there's some other fermions, sterile neutrinos that we haven't seen that are also massless. And we can use those to cancel the Casimir contribution of the photons and gravitons. Well, you can do that. But the problem is that we have all the other particles of the standard model with their extremely complicated interactions and everything else. And at least every time I've tried to see if it's possible to add partners to them of things that we haven't seen that precisely cancels all of the radius dependence of the Casimir energy on a circle, I've proven that it's impossible. Okay? So you can't do it on a circle. It's still possible you could do it on an interval. This exercise I haven't done. I think it's a great exercise it's a very nice thing to think about. In general, we can imagine that in this picture you're opening up a large interval, and there's things that even are localized to the ends of this interval with the standard model plus any additional matter in here that interact somehow with things at the end. And the goal is to see, is there any way you could add with any fine tuning you want? The problem isn't tuning. That's the whole point, is that things that would appear like tunings here, which are guaranteed from the supersymmetry on the other side. But even with tuning, is it possible to add a particle content that completely cancels the Casimir energy at all values of the length of that interval? I believe it is impossible, but I haven't proven that it is impossible. Okay? So, but that gives you at least a flavor for at least a set of words for other possibilities for what might be solving these tuning problems that don't involve new physics at high energy scales, but they do involve, in this case, a load of predictions for low energy physics of tunings that aren't just the tuning you're talking about, but many other tunings as well. Anyway, so this is one example. There are a number of others, but I won't go into the rest of them. We can talk about it. We talk about it at a later time. But just to say that people have been thinking about. People have thought a lot about the hierarchy problem. Haven't been dogmatically pursuing either standard, SUSY, naturalness, extra dimensions. By the way, those things that are standard didn't used to be standard. So at some point in time, people had to think about them. And then jumping to anthropics, which means no rules. Quite the contrary. In fact, you can't do anything you want. There's still rules, even though the rules are different. And even crazy things. Okay, and perhaps we'll be forced into thinking about more crazy things. The only thing I could imagine that would force me personally to go back and think these much more radical thoughts is if we saw something like not just the Higgs, but a bunch of Higgses, a bunch of other scalars, a bunch of other light stuff with zero environmental purpose in life. And if we saw that, I think that's the thing that would convince me that 99% of the effort thinking about naturalness, either in the direction of anthropics or in the direction of standard naturalness, has been wrong. If we just see a light Higgs, it seems perfectly reasonable from the point of view of anthropics, even though we won't be able to approve it. And obviously, if we see lots of new light superpartners or any other natural physics, we'll know what we're doing. So anyway, that's all I want to say. Let me just say again that for all the reasons mentioned in this talk and other ones too, even though I don't know whether it's going to be natural or not, the issue of naturalness, the fact that we have something that on the face of it has only ever been seen in nature before with extreme fine-tuning, makes the question of naturalness to my mind, the central thing about what we've seen in particle physics, which is novel, which is new, which has never been seen before. People keep talking about wanting to see new physics, and if by new physics you mean new phenomenon that have never been ever seen anything like it in nature before, then just the Higgs qualifies as dramatic new physics. We've never seen anything like it. And had we been so unlucky to have something like good old-fashioned Technicolor describe electroweak symmetry breaking, then when my condensed matter theory friends ask, what's so special about your effective theory? And I say, oh, it's the vacuum of our universe. And they're like, big whoop, right? So what's special about its properties? Does it have any interesting structure, interesting dynamics? Oh, just some weakly coupled effective theory, really? Wow, like any idiot can calculate its Feynman diagrams. And had it been something like Technicolor, of course, then it would have been weakly coupled. But anyway, had it been something like a Technicolor, the answer would be, no, it's not all that special. It's just like tons of theories you guys have seen in the lab. Okay? And yes, it's relativistic, there's strong dynamics and so on, but it'll be like peeling back the layers of the onions. It would be like the strong interactions all over again. I would be very depressed. I would have felt like I wasted 20 years of my life had it ended up being something like a Technicolor, because there would not actually be anything particularly special about it. But it isn't. It isn't. It's shocking that it's something like the Higgs. It's absolutely shocking that it's something like as simple as the Higgs. We've never seen that before. The reason we've never seen it anywhere else in nature before is that elsewhere in nature, it definitely takes fine-tuning. So whether its lightness, now that we've seen it, is a consequence of fine-tuning, a consequence of the fact that we have dramatic things like supersymmetry or extra dimensions or whatever really big new physics generating the scale, or evidence for something even more radical, much more radical paradigm shifts than any of the ones that we were thinking about before, that we don't know. But I do strongly think the issue is by far the most important issue that we're facing in particle physics today. Thanks a lot.
Given the lateness of the hour, let's have all questions for Nima. You come up, and anyone that wants coffee, it might still be out there. It's through the art gallery on the back patio, not the second floor this time. And we'll definitely have wine and cheese at 5:30, and let's start in half an hour for the panel.